Hello, this is the section 6.2 lesson. Chapter 6 is on the topic of regression, and in section 6.2 we introduce one of the building blocks of this idea of regression, and that's the idea of correlation. Now there's some theory involved with this section, but in this lesson we're not going to get too in-depth in that theory. We're going to focus on conceptual understanding and interpreting those ideas from a practical standpoint. So in section 6.1 we introduce some of the fundamental questions that we try to answer in this chapter. So often in life we ask questions about relationships. For instance, we might ask, is weight somehow related to heart disease? Or is time spent studying for a standardized exam related to scores? Or another example, is the number of home runs hit in a ballpark related to the altitude of the park? Well, if we take a step back and look at what's going on here, for instance, weight of a person. Well, that's a variable, right? Everyone's weight is a little bit different. Time spent studying, that's a variable. Everyone spends a little bit different time studying. Score, that's a variable. Number of home runs hit, that's a variable. Altitude, that's a variable. So fundamentally, all these questions are about relationships between variables. So if we take a step back and think about some fundamental questions we might ask about variables, number one is there a relationship between two variables? In fact, that's really what all three of these questions up here are asking in a fundamental sense. Is there a relationship between two different variables? Second question we might ask is how strong is that relationship? If there is a relationship, how strong is it? And another question, can we predict the value of one variable if we know the value of the other? So for instance, if I know the number of home runs hit in a ballpark, could I predict the altitude of that park, or maybe vice versa? And so these are three real-world questions that we might ask, and in this chapter we are going to introduce some mathematical tools that we can use to help answer these questions. Now in this section we're going to focus on answering these first two questions. In section 6.3 we're going to focus on the third question. Okay. So to illustrate these ideas, let's look at this example. Consider the random experiment of choosing a student and measuring his or her shoe length and overall height. So their shoe length, that's a variable, right? Everyone's shoe length is a little bit different. And then overall height, that's also a variable. So we got two variables involved here, so let's give them names. Specifically, these are random variables. It's random because we randomly choose a student, and everyone's shoe length and height is going to be a little bit different. So let's let x equal the shoe length and y equal the overall height of that person. Now some specific questions we might ask about this scenario are, number one, how is height related to shoe length? Or in terms of x and y, how is x related to y? Number two, how strong is that relationship? So if there is a relationship between x and y, just how strong is it? And then number three, if we know a person's shoe length, can we predict his or her height? Or in terms of x and y, if we know the value of x, can we predict the value of y? So these are the types of questions that we're going to be trying to answer here in this chapter. This section is going to be these two questions. The next section will be the third question. So in order to answer these questions, we need to observe some values of x and y, meaning we need to go out and collect some data. Specifically, what we need to do is measure shoe length and height of some different students. And so that's exactly what I did here. So the author, that's me, had 10 of his students measure their shoe length and their height. Actually, I did this with more than 10 students. I just picked my 10 favorite students and put their data here. So the first student had a shoe length of 9 inches and a height of 62 inches. Second student had a shoe length of 10 inches and a height of 64 inches, and so on and so forth. So here what we have are 10 observed values of x and y. Now notice that our data come in pairs. Every student gave me two numbers, a shoe length and a height, and those numbers have to go together. So let's take our first question. How is height related to shoe length? And we can answer this question with a really simple graph. what we're going to do here is just plot each pair of numbers. We're going to have a horizontal axis for our x values, that's shoe length, a vertical axis for our y values, that's height, and then we plot each pair of numbers. So here's one student, here's another student, third student, fourth student, so on and so forth. Okay. So there's a simple graph of our data, and we can use this graph to answer our first question: is there a relationship between these two variables? Well, let's make a couple of observations here. First of all, if we move from left to right, the shoe length increases, and look what's happened at the same time. The height also increases. So as shoe length increases, height also increases. Also note that these dots form kind of a straight line. Not a perfect straight line, but kind of a straight line. And so the answer to our question is there is a positive linear correlation between our variables x and y. Now let's parse this out a little bit here. The word correlation is just a fancy term for relationship. Linear means straight line, and positive means that that slope slopes up from left to right, or has a positive slope. And so again, there's the answer to our first question. Is there a relationship between these two variables? Yes, it appears that there is a positive linear correlation between x and y. Okay. Now let's look at some other types of correlations between some other sets of random variables. Okay, so here's a set of data from some other variables, just generically called x and y. So again, we put our x values on the horizontal axis, our y values on the vertical axis, and look at the pattern that's formed here. These dots form kind of a straight line that slopes down from left to right. So in this case, we would say that these two variables have a negative linear correlation. If we look at this example right here, again, we've got some other variables, x and y. Again, we plotted x on the horizontal, y on the vertical. Notice that there's a pattern here, but it's not a straight line pattern. So we would say that these variables have a nonlinear correlation. Here's another set of data, another variables x and y, again x on the horizontal, y on the vertical. And look at the pattern here of those dots. There just really isn't a pattern. Not a straight line pattern, not a nonlinear pattern, just no pattern at all. So these variables, we would say they have no correlation. So to determine if there is a relationship between variables, we can start off with a simple scatter plot like this. Now, the next question that we asked is, well, how strong is that relationship? Well, we can try to answer that question with this idea of correlation. And the theoretical answer to that second question is given in definition 622, where we define the correlation coefficient of x and y is given by this somewhat rather nasty looking formula. So correlation coefficient is denoted rho. This is the Greek letter lowercase rho of x and y. That just tells us the names of our variables. And is calculated by taking the expected value of the product xy minus the mean of x times the mean of y divided by the standard deviation of x times the standard deviation of y. This correlation coefficient is also called the population correlation coefficient. We could think of this as measuring the strength of the relationship between height and shoe length in the population of all students. Okay? So this is a theoretical answer, but it's not a real practical answer, because in order to calculate this quantity, I would have to know the mean of x, the mean of y, their standard deviations, and I'd also have to know the joint distribution of x and y in order to be able to calculate this expected value. So this is a fine theoretical answer, but it's not a real practical answer. So we're never going to be able to calculate this exact population correlation coefficient. Instead, we're going to have to try to estimate it. And so we're going to estimate it with a quantity called the sample correlation coefficient. And in order to estimate or to calculate this correlation coefficient, we have to go out and collect pairs of data, like we've already done. And then we're going to calculate it using this somewhat rather complicated looking formula. So this sample correlation coefficient is denoted R, and it says we take the number of data values times, then we take each x value times the corresponding y value, add them up. and then we take all the x values, add them up. All the y values, add them up. Down here we square each x value, add them up. Here we take all our x values, add them up, and then square it, and then we do all this nasty looking arithmetic. So this sample correlation coefficient is also called the Pearson correlation coefficient, named after a man named Pearson who did some pioneering work in statistics during the early 1900s. Now, an important point to remember about this sample correlation coefficient, R, is that it is an approximation of our population correlation coefficient, rho. Just like back in chapter 5, when we talked about statistics, we said that sample statistics are approximation of our population parameters. Here, R is a sample statistic, rho is a population parameter. So this statistic is an estimate of this parameter. So R is an approximation of rho. They aren't identical. They aren't exactly the same, but they are very similar. Okay. So let's look at just real quickly how we could calculate this by hand if we wanted to. So here in this table, I've listed all my pairs of data. Here's my formula. So for instance, one thing I need to do is take each value of x times y and add them up. So that's what we do here in this column. We take 9 times 62 to get 558, 10 times 64 to get 640, and then we add those up. So this number right here is this quantity right here. Next, we need to add up all the values of x. Well, that's given right there. Add up all the values of y. That's right here. This says we need to square each x value, add them up. That's what we do here. We square each value, add them up. So this number is this quantity right here, and so on and so forth. So when you plug in all those numbers to our formula here and do this rather nasty looking arithmetic, we get this result right here. Now this looks all very tedious, but luckily this is all going to be done on the calculator, so we're not going to have to do any of this by hand. We'll get to the calculator here at the end of this lesson, but let's just take this result for granted right now. So there's the value of our sample correlation coefficient. So now the next question is, well, what does that mean, right? What does that sample correlation coefficient tell me? Well, the answer here is really given in theorem 622, which is a theoretical result, and it's stated in terms of rho. Whenever you see rho, think R, because R is what we actually calculate. So let's talk about this theorem, and then we'll talk about what it means in a more practical sense. So number 1 says that the absolute value of rho is always less than or equal to 1. Number 2 says that if our variables are independent, then rho is equal to 0. And the third one says if the absolute value equals 1, if and only if y is equal to mx plus b for some constants m and b. So what this theorem means in practical terms, number 1, rho is between -1 and +1, means that r is always between -1 and +1. Number 2 says that if r is close to 0, then there is no relationship between x and y. Remember, this idea of independence means that one just isn't related to the other one. So if I get a value of r close to 0, that indicates there just is not a relationship between x and y. The third one is maybe the most important one, which says that if r is close to -1 or +1, then there is a strong linear relationship between x and y. So remember what linear means graphically means straight line. In mathematical terms, linear means that one variable equals a constant times the other variable plus another constant. Y equal mx plus b. This looks like the formula for a straight line back from high school algebra. So if r is close to -1 or +1, there's a strong linear relationship between x and y. So let's kind of summarize these results here in a couple of important points. Number 1, r measures the strength of a linear relationship. And the closer r is to +1 or -1, the stronger the linear relationship. So in terms of a number line here, if we have r value close to -1, we'd say that it has a strong negative correlation. If it's close to +1, we'd say there's a strong positive correlation. If r is close to 0, we'd say that there's no correlation. So let's illustrate this idea with a few examples. So here we have 4 different sets of data. for 4 different pairs of random variables. Let's take this pair of random variables here, and notice the scatter plot here. These dots form kind of a straight line that appears to slope down from left to right. So graphically, there's looks like a strong negative linear correlation. Well, if we were to calculate the value of r for this data, we would get negative 0.931. Now, we obviously can't tell that just by looking at the data that this is the value of r. You just have to take my word for it. But we see there that's a value of r that's close to negative 1, indicating again a strong negative correlation. Here we see these dots form kind of a straight line that slopes up from left to right, but it's not a very strong straight line. So it looks like there's a weak positive correlation. And the value of r for this data is 0.65. See, it's positive, but not very close to positive 1. If we look here at this data, we see that these dots are just kind of randomly scattered. There doesn't appear to be any relationship. The value of r there is 0.147, so very close to 0. Again, I mean no linear correlation. Now here, if we look at this, we see that there is a relationship, but it's a nonlinear relationship. Now we can go ahead and calculate a linear correlation coefficient, but it's really meaningless because there is not a linear correlation. So the fact that this is maybe a somewhat positive number is kind of irrelevant. Okay. So a linear r measures the strength of a linear relationship. It doesn't measure the strength of a nonlinear relationship, just a linear relationship. Okay. So let's go back to our shoe length data. Here is our scatter plot where again we saw our strong positive correlation. Here was our value of r, again very close to 1. And so based off of those two observations, we would interpret them by saying that there appears to be a strong positive linear correlation between shoe length and height. Okay? That's supported by our graph. It's also supported by our very large value of r. Well, we can more formally justify this interpretation using a hypothesis test. Specifically, we're going to test the claim that rho, our population correlation coefficient, is positive. And we can do this in much the same way as our other hypothesis test that we talked about in Chapter 5. So the hypotheses that we're going to test here are the null is that rho equals 0, and the alternative is that rho is greater than 0. Remember, the null hypothesis is kind of a statement of the status quo. It's what we might expect to be true if we didn't have any data to indicate otherwise. So without any data, we might think that there's no relationship between these variables. But our data suggests that rho is greater than 0, so that's going to become our alternative hypothesis. Now, informally, what these hypotheses mean is that, well, if rho equals 0, that means things are independent, which means that there's no correlation in the population. If rho is greater than 0, so that means that there is a positive linear correlation in the population. So we're testing the idea of no correlation versus there is a positive linear correlation. Now the hypothesis test here is called simply a t-test, and the purpose is to test the null hypothesis that rho equals 0, which is exactly what we have here, where x and y have a bivariate normal distribution. Now this qualifier of bivariate is explained more in the book. We won't go into it here. We'll just take it for granted that these two variables have a bivariate normal distribution. So our test statistic is given by this rather simple formula. Notice all we need there is the value of r and the value of n. The p-value is an area underneath a student t-density curve with n-2 degrees of freedom. And whether that's an area to the left or the right depends on the form of the alternative hypothesis, as we did back in Chapter 5. So going back to our shoe length data, let's formally test our claim that rho is greater than 0. So here was our value of r. We had 10 data values. Here was our null and alternative hypotheses. So we calculate our test statistic. There's r, there's n, there's r again. We do all that arithmetic, we get 12.16. Now the p-value is the area to the right of this test statistic under a student t-density curve with 8 degrees of freedom. Now we know it's an area to the right because this is a right-tailed test, and using software, we can show that this p-value is about 0. We'll justify it. We'll show how to do that on the calculator here in a bit. But you can imagine that this p-value is pretty small because this test statistic is rather large and the area to the right is going to be pretty small. So let's interpret that p-value. Well, we interpret it in the exact same way as every other p-value. We compare that to our significance level. None was given this problem, so we use the default 0.05. So the p-value is definitely less than alpha. And so our technical conclusion would be to reject the null hypothesis. Now our final conclusion. Remember, we reject the null hypothesis in favor of the alternative. The null is that there is no correlation. The alternative is that there is a linear correlation. And so our final conclusion would be that there does appear to be a positive linear correlation in the population. So our data indicated that there was a positive linear correlation in the population. Our hypothesis test further justifies that. Now, what that final conclusion means in a practical sense is that we're going to be able to use a straight line to predict height in terms of shoe length. Now, we're not going to talk about how that's done here in this section. We're going to get to that in section 6.3. But that's the practical significance of this result. Now, lastly, let's talk about how to calculate R and our test statistic and our p-value on the calculator. The first thing is to enter our data. And so we're going to go to the Stat Edit menu where we get our data editor. We're going to enter our x values in L1, our y values in L2. So these are our shoe lengths and these are our heights. Next, we're going to go to the test menu and scroll up or down to option F, linreg t-test. Now, if you have a TI-83 calculator, it will be option E, but it's still called a linreg t-test. Linreg stands for linear regression. T-test means that we're going to do a t-test. And so you're going to get a window that looks like this. We're going to first enter the name of our X list, which should be the default should be L1. Next is the Y list. Again, the default should be L2. Frequency, all of is 1. And then in this row, we're going to enter the form of our alternative hypothesis. Now this gives us two parameters, beta and rho. We'll talk about beta in later sections, so just kind of ignore beta right now. So our alternative hypothesis was that rho is greater than 0. So we're going to choose that one. REGEQ stands for regression equation. We're going to talk about that in next section. For right now, you can either leave this blank or whatever value's there. It doesn't really matter. And then lastly, select Calculate, press Enter. And you should get a window like this. So we see that we did the linreg t-test. Now this result right here we're going to talk about in next section, so just ignore it right there. Next row gives us the form of our alternative hypothesis, exactly what we want. Right here is our test statistic, exact same thing that we got by hand. And right here is the p-value, 9.6 times 10 to the negative 7th. So this is really, we have 6 zeros in front of the 9. So it's a really, really small p-value, practically 0 for all practical purposes. Next, it gives us the appropriate degrees of freedom, which is 8. And then next, it gives us A. We'll talk about the meaning of A in next section. But you see that there's some more results. So if we scroll down, we get a window that looks like this. Here it gives us the value of B, which again we'll talk about in next section. Here's the value of S. We'll talk about that later. The important result here on the bottom is the last line, R equals 0.974. That's our correlation coefficient. Notice that's the exact same thing that we got by hand. Now right above that it gives R squared, which is just the square of the R value. You can verify this number by just squaring the R value and you get that exact same number. So that's all there is to calculating the correlation coefficient, the test statistic, and the p-value.